Okay, so in this talk, I will be talking about immersed special Lagrangians in Lagrangian mean curvature flow. So in particular, I'm going to explain a construction of a long-time solution to Lagrangian mean curvature flow that starting from an embedded Lagrangian submanifold, and as t goes to infinity, it converges to an immersed special Lagrangian submanifold. So this is kind of an infinite time singularity. So in the first part of this talk, I will give a brief introduction to special Lagrangians in Lagrangian mean curvature flow. So recall that a submanifold is minimal if its mean curvature vector vanishes identically. And by the first variation of volume, one can show that actually the mean curvature vector plays the role of the negative gradient vector field of the volume functional, and therefore the minimal submanifolds are critical points of the volume functional, and therefore they are not necessarily volume minimizing. For example, you can consider the great circles on a two-sphere, and they are minimal, but clearly they are not volume minimizing. So if we deform the submanifold in the direction of its mean curvature vector, then this is called the mean curvature flow. So if we regard the mean curvature vector as the negative gradient of the volume, then the mean curvature flow is just the negative gradient flow of the volume functional. So it is the most efficient way to decrease the volume of a submanifold. Therefore, people hope that the mean curvature flow can be used to find volume minimizers in a Riemannian manifold M. Next, I explain the special Lagrangian submanifold. So this kind of submanifolds live in Calabi-Yau manifold, which is a quadruple Mg J omega, where Mg is just a Riemannian manifold, and J is a compatible, almost complex structure, such that if we put this J into the first position in the metric, you will get a closed-to form called the Kähler form or the symplectic form of M. And this capital omega is a holomorphic M0 form on M, satisfying this normalization. Okay. So due to the existence of such a compatible complex structure J, the ambient manifold M must be even dimensional. And therefore, it makes sense to consider a half-dimensional real submanifold inside M. So we say this submanifold is Lagrangian if we pull back its Kähler form equal to 0. In this case, one can show that if we pull back the capital omega, then what you get is some unit complex number times the volume form of L, assuming L is oriented. Here we can write this unit complex number as e to the I theta L, where theta L is the phase of this complex number called the Lagrangian angle. If furthermore there exists a constant theta bar such that if we rotate the capital omega by e to the minus I theta bar, take the imaginary part and pull back to L, you get 0, then L is called the special Lagrangian. So a special Lagrangian submanifold is a Lagrangian submanifold with this additional special condition. And in this case, one can show that if we pull back the real part of this rotated capital omega, then you will get the volume form of L. And so this property is called the calibrated property. So in particular, a calibrated submanifold must be volume minimizing due to a simple Stokes theorem argument. And therefore, special Lagrangian submanifolds are volume minimizers in Calabi-Yau manifold. But so far, there's no general existence theory for special Lagrangians. But since they are volume minimizers, so people hope to use the mean curvature flow to construct special Lagrangians in a Calabi-Yau manifold. Okay, now it makes sense to consider the mean curvature flow of Lagrangian submanifolds. So let's start with Lagrangian submanifolds and consider the mean curvature flow starting from this initial data iota naught. So small trick shows that if the initial data is Lagrangian, then as long as the flow exists, the submanifold is still Lagrangian. So this justifies the name Lagrangian mean curvature flow in the title of this talk. So using the Lagrangian condition, one can show that the mean curvature vector is actually the J of gradient theta L. So the gradient theta L is a tangent vector field. Then by Lagrangian condition, one can show that if you apply J to a tangent vector field, you get a normal vector field. And this nice identity shows that the mean curvature flow is an infinitesimal Hamiltonian deformation. And therefore, the solution stays in the same Hamiltonian deformation class as the initial data. Okay, and a Lagrangian submanifold L is called master of zero if the cohomology class of d theta is equal to 0. So if L is master of 0, then one can lift its Lagrangian angle to a real value function on L. And L is called the almost calibrated if the oscillation of theta is less than pi. And there's a very nice equation for the Lagrangian angle along the mean curvature flow is that the Lagrangian angle satisfies the heat equation. And therefore, by maxima principle, all these properties like master of zero and almost calibrated properties are preserved on the mean curvature flow. Okay, so the mean curvature flow of Lagrangian submanifolds seems to have some nice properties. Okay, so the main conjecture or the guiding principle in this field is the Thomas-Yau conjecture. And roughly speaking, Thomas-Yau program is trying to establish an existence theory for special Lagrangians in the style of the Donaldson-Uhlenbeck-Yau theorem, the existence theory for Hermitian-Young-Mills connections. So the conjecture that there should exist a stability condition on the space of Hamiltonian deformation classes such that if you start from a Lagrangian representative of a stable class, then the flow should exist for all time and converge to a unique special Lagrangian representative. In the second part of the conjecture, saying that if you start from a general object, not necessarily belongs to a stable class, then the flow should produce kind of Harder-Narasimhan filtration for this class L. So the first part is sort of a condition to guarantee the long-time existence and convergence of Lagrangian mean curvature flow. And the second part is kind of starting some kind of singular behavior of the flow that break a Lagrangian submanifold into smaller pieces. And there has been some modification of the original statement of Thomas-Yau conjecture due to Dominic Joyce and recently by Yang Li. Okay, so the second part of this talk will be about the gluing construction of special Lagrangians. So I mentioned about this singular behavior of Lagrangian mean curvature flow that may break a Lagrangian submanifold into pieces. And so, but this theory is not well studied yet. So we try to look at some model case, and especially in the special Lagrangian category, this kind of theory, singularity theory, has been established pretty well. So in particular for the simple kind of singularities. So the main reference of this section will be Dominic Joyce's series of papers on the special Lagrangian submanifolds with isolated conical singularities. Okay, so if you want to see more details of this gluing construction of special Lagrangians, then you can read Joyce's paper. So to start with, we need to introduce more concept from symplectic geometry. So now we don't use the Riemannian metric and the complex structure and holomorphic M0 form. So we only take M and the Kähler form omega. And this is a symplectic manifold. The first thing we have to use is the Darboux theorem, saying that at each point of the symplectic manifold, if we fix an isomorphism from C to the M to the tangent space of that point, such that the symplectic form is preserved, then we can sort of extend this property to a neighborhood of X. Namely, there exists a smooth map from a ball in Cm centered at 0 to M, such that the origin is mapped to X, and the differential of this map at the origin is equal to this isomorphism V. And the thing is that throughout this neighborhood of X, the symplectic form is preserved. Here, this omega prime is the standard symplectic form on the complex Euclidean space Cm. So the next theorem is basically kind of a generalization of Darboux's theorem. So now we get a Lagrangian submanifold. Then the Weinstein theorem says that there exists a smooth embedding from the open neighborhood of the zero section in the cotangent bundle of L to M, such that if we restrict this map on the zero section, you get the immersion of L. And the symplectic form is preserved. Here, the omega hat is the canonical symplectic form of the cotangent bundle. So a consequence of Weinstein's Lagrangian neighborhood theorem is that one can show that any nearby, like closed in C1 sense, a Lagrangian submanifold to L can be identified with the image of a smooth closed one form. So it's basically, you can identify the nearby Lagrangian submanifold as some graph of closed one form over L. This is the picture illustrating Darboux theorem and Weinstein theorem. Okay. So let me introduce you the special Lagrangians with isolated conical singularity. So we start with a special Lagrangian cone, so which is the cone in the Euclidean space C to the M with link sigma j. Okay. So for each j, we get a special Lagrangian cone with this immersion. Then we say a special Lagrangian x in M is a special Lagrangian with isolated conical singularities x1 to xn and cones c1 to cn with rates gamma 1 to gamma n if x prime, which is x minus these singular points x1 to xn, is a smooth special Lagrangian, and for each j, you can find an open subset Sj in x prime such that this Sj lies in the image of a Darboux coordinate chart gamma epsilon j around where this epsilon j is a Darboux chart around xj. And there exists a phi j, which is a map from the cylinder to this Darboux coordinate chart, such that we compose this phi j with the Darboux map, you get diffeomorphism from the cylinder to Sj. And this phi and the standard immersion of the cone satisfy this decay property. So this is a picture illustrating the definition of special Lagrangian with conical singularity. So here we get a cylinder, and this x is the special Lagrangian with conical singularity. So at near each singular point xj, we have a open neighborhood Sj, such that using the Darboux coordinate chart, you can see that in the Euclidean space, this Sj is just the image of some map phi j. And when you compare these two, the image of phi j with the image of the cone, then these two graphs has some nice decay condition. Okay, so next I introduce you the asymptotically conical special Lagrangians. So again, we were given a special Lagrangian cone C with immersion alpha C. So we say L is a special Lagrangian submanifold asymptotic to this cone C and rates delta if there exists a compact subset on L and number R such that and a diffeomorphism phi from this cylinder to L minus K, such that if we compare this diffeomorphism with the immersion of the cone, you get this decay condition. Okay, so in this picture, you see that we have two different. So after subtracting a compact subset K, we can compare the images of this phi and the standard immersion of the cone, and these two graphs has this nice decay condition. Okay, so then if we got a special Lagrangian with isolated conical singularities, and if we also get some asymptotically conical special Lagrangians with the same asymptotic cone and with certain range of rates, then there's a standard Lagrangian surgery construction which desingularizes the singularities x1 to xn using some scaled asymptotically conical special Lagrangian L1 to Ln. So the point is that the end Sj of x prime and Lj are both close to the special Lagrangian cone. So by this Werenstein's theorem, one can identify these two submanifolds with graphs of closed one forms on the cylinder. So using the decay condition, one can actually show that these one forms are not only closed but exact. So we can then interpolating the potentials of these closed one forms to get a smooth exact one form, which sort of glue this Sj and scaled asymptotically conical special Lagrangian together. And in this way, we construct a smooth Lagrangian submanifold n epsilon in M. So this n epsilon is just Lagrangian, but not special Lagrangian. So this is a picture illustrating the gluing construction. So we get this special Lagrangian submanifold with conical singularities, with two conical singularities, and we try to glue in this asymptotically conical special Lagrangians into this a small neighborhood of the singular points. So basically, we remove the blue parts from both kind of submanifolds, and then we interpolate the potential functions in the red regions. So in this way, we get a smooth Lagrangian submanifold in M. And actually we get a one parameter family because we can adjust the scale of the asymptotically conical special Lagrangian to be as small as we like. And when the scale goes to 0, the submanifold n epsilon converge back to the original the special Lagrangian with conical singularities. Okay, so the submanifold n epsilon constructed by the Gruen construction is just Lagrangian, but it's also close to being special Lagrangian. So we hope to perturb this n epsilon by a small exact one form du such that we get a genuine special Lagrangian submanifold. So using the Lagrangian neighborhood map capital phi n epsilon by Weinstein's theorem, we let the new perturbed submanifold be n epsilon du. So yeah, so the n epsilon du is just sort of the graph of du over this n epsilon. So we want to show that this perturbed submanifold n epsilon du is a special Lagrangian with phase 0. So in order to do that, we need to solve a fully nonlinear PDE, which is Lagrangian angle of n epsilon du equal to 0. So we can do the Taylor expansion to the first order, then we get roughly this expression, namely the Lagrangian angle of n epsilon du is roughly the Lagrangian angle of n epsilon plus the Laplace of u, and then plus some quadratic error term. So to solve this equation, roughly speaking, we will need to invert the Laplace operator for all small epsilon, such that the inverse of the Laplace operator is bounded uniformly in epsilon. So this kind of estimate could fail if there exists so-called small eigenfunctions whose eigenvalues goes to 0 as epsilon goes to 0, because in this case the inverse of Laplace operator goes to infinity as epsilon goes to 0. So we don't have a uniform bound for the inverse. Okay, so let's state Joyce's theorem. So if x prime is connected, then we can always perturb this n epsilon into a special Lagrangian by a small exact one form for epsilon small enough. So this connectedness is very important here. Since if x prime is not connected, then say it's got n prime connected components, then they exist in n prime minus one dimensional linear subspace of small eigenfunctions. So that is to say, our Laplace operator don't have bounded inverse on this subspace. So in this case, we need an additional condition, which I call the balancing condition, in order to make this perturbation argument works. So if the balancing condition holds here, then one can perturb an epsilon into a special Lagrangian by a small exact one form. So here I don't give the exact statement of this balancing condition, because otherwise I need to explain a lot more terminologies. But we will see this condition in a special case later. Okay, so let's look at the special case, which is that the assume our special Lagrangian with isolated conical singularity is actually an immersed special Lagrangian, and satisfy some properties, some additional condition on the angles of the tangent planes of each immersed point. Okay, so let me explain this now. So suppose X is a compact immersed special Lagrangian, then for each transverse self-intersection point x1 to xn, the pre-image has 2 points. Okay, so let's assume this immersed special Lagrangian only has this kind of immersed point that is modeled on transverse intersecting planes. So each immersed point has got exactly two pre-images. So the tangent plane at the pre-images is a union of planes in Cm. Then we assume that up to a SUN rotation, we can put these two planes into this kind of special form. So we can rotate one of the planes to the real plane in Cm, and at the same time, the other plane can be written in this way. So we rotate each coordinate by e to the I phi 1 to e to the I phi m, such that the summation of phi's is equal to pi. So this is some kind of additional assumption to allow us to do the desingularisation. Then this X can be regarded as a special Lagrangian with isolated conical singularities with cones, the union of planes, and rate equal to 3. Okay, so to desingularize such an immersed special Lagrangian, one need to find a suitable asymptotically conical special Lagrangian which has this cone, which is asymptotic to a cone, the union of two transverse intersecting planes. Okay, so we are given a sequence of angles phi 1 to phi m, such that the sum of the angles is equal to pi. Then there exists an asymptotically conical special Lagrangian, which I denoted by L phi a in Cm, with the cone being the union of these two planes, where pi naught is the real plane Cm, and this pi phi is the plane in this form. Okay. So this kind of asymptotically a conical special Lagrangian is called the roller neck. So the roller neck is diffeomorphic to Sn-1 cross R. So it's kind of a neck or a cylindrical thing. So it can be thought of as a Lagrangian analog of catenoid. Here, this capital A is a positive number, is the scale of this roller neck. And as A goes to 0, this roller neck converge to this pair of planes in some suitable sense. And one can show that this roller neck is exact, namely, if we restrict the Liouville form on the roller neck, we get an exact one form on L. So Imagi, Joyce, and Oliveira shows that the roller neck is a unique, exact asymptotically conical special Lagrangian with this cone and negative rate up to scaling. So we can use the roller neck to desingularize the immersed points of an immersed special Lagrangian satisfying the angle condition. Okay, so this is a picture illustrating this desingularisation. So here we get these two planes intersecting transversely at the origin. So the roller neck is this red submanifold, and roughly speaking, the volume of this central ball is equal to this capital A. Okay, so if we got an immersed special Lagrangian here, then if each tangent planes at the immersed point satisfy this angle condition here, then we can glue this roller neck into a neighborhood of the immersed point to get an embedded Lagrangian submanifold n epsilon. Okay, so then we can state the Joyce's theorem in this special case. So if we remove all the immersed points x1 to xn is still connected, then we can construct a family of embedded special Lagrangian n epsilon tilde such that n epsilon tilde converge back to x as epsilon goes to 0. And suppose the kinetic component of x prime is greater than 1. So we got several kinetic components. Then they exist. Suppose so this is the balancing condition that I mentioned earlier. So suppose there exists A1 to AN, which are positive numbers satisfying this identity. So this, you can see that still is a bit complicated, but so suppose this condition holds. Suppose we can find this A1 to AN, then there exists a family of embedded special Lagrangians n epsilon tilde such that it converges to X as epsilon goes to 0. Okay. So this is the balancing condition I'm referring to. Okay. So this is, I want to show you the kind of connectedness using the picture. So we've got this first case, which is the good case, that we don't need a balancing condition, is that we remove the immersed point, we get a connected X prime. But we have also this disconnected case, that when we remove the immersed point, we get disconnected X prime. So in this second case, we will need additional balancing condition to guarantee the existence of this perturbation. Okay, so let me briefly kind of describe the idea of this balancing condition. So we take a closer look at the simplest obstructed case. Okay, so namely, we assume we have an immersed special Lagrangian with only one self-intersection point, and we get two connected components. So in this case, the balancing condition reduced to finding a positive solution to A equal to 0, which is impossible. Therefore, one cannot desingularize X by using gluing roller neck with positive scale. Okay, so here is the heuristic reason. The first eigenvalue of the plus operator is this order. So you can see that the inverse of the plus operator is not bounded uniformly in epsilon. However, the second eigenvalue is bounded uniformly from below. So we can show that the plus operator has bounded inverse on the orthogonal complement of the kernel in the first eigenspace. So here you can sort of visualize the first eigenfunction. So the first eigenfunction can be approximated by sort of interpolating constant functions on each kinetic component using a harmonic function on the roller neck. So if we put constant function d1 on x1 and constant function d2 on x2, then there exists a harmonic function on the roller neck, which is asymptotic to d1 on the one end and d2 on the other end. So we can sort of define a function in this way, and we can show that this kind of function approximates the first eigenfunction of the Laplace operator. Okay, so if we project the Lagrangian angle of an epsilon onto the first eigenspace, then we will see that the coefficient will be given by some big O of epsilon to the m times the size, the scale of the roller neck A. Okay, so we will see that this causes some trouble when we want to do the iteration. So roughly speaking, we would like to solve this equation by iteration, where this Q is the quadratic error term appeared earlier in the Taylor expansion of the Lagrangian angle of n epsilon du. So to do the iteration, we would like to find a fixed point of this map. So this map P epsilon sends u to the minus of Laplace inverse applied to theta plus q du. So you can see that a fixed point of this map gives you the solution to this equation, right? Okay, so now we have uniform bound of the inverse of Laplacian on the orthogonal complement of the kernel and the first eigenspace, right? And on the first eigenspace, the inverse of Laplace operator rolls up like this. Okay, so if we want to measure the norm of P epsilon applied on U in terms of some weighted norm, then we'll see that we get this Lagrangian angle of this n epsilon plus some small term times the norm of U plus this O1 times A. So the last term here is not small when epsilon goes to 0, while the first two terms goes to 0 as epsilon goes to 0. So to find a fixed point of this P, we need to sort of control the size of the image of P. And unfortunately, we get this non-small term, which we cannot make it smaller by making epsilon small enough. So this is the obstruction to this iteration procedure. So to make the iteration work, this capital A must be 0, which is exactly the balancing condition in this simplest case. Okay, so in the last part of this talk, I will be talking about our recent result joined with Zhongren Cai and Albert Wood on the infinite time lower neck pinch. So we use the setting of the previous slides. Namely, we have a compact immersed special Lagrangian with only one self-intersection point, and X prime has two kinetic components as before. And we assume that the tangent planes at this self-intersection point satisfy the angle condition that the sum of the angles is equal to pi, so that we can desingularize the self-intersection point using the roller neck. But now we assume the gluing scale epsilon is dependent on some time parameter t, where t belongs to an infinite interval from lambda to infinity. So for each t, we get number epsilon of t, so we can still construct the desingularisation and epsilon t as before. Okay. So this time we are not going to solve the special Lagrangian equation. Instead, we want to solve that. Can we perturb this family and epsilon t by a time-dependent exact one form, such that the perturbed family of submanifolds satisfy the Lagrangian mean curvature flow? Then if we do this, then we can see that this perturbed family satisfies the Lagrangian mean curvature flow if and only if U satisfy this fully nonlinear equation. So we get some extra term C here and the extra term dtu here, because U depends on T now, and this C is basically the potential of the speed of the n epsilon t. So because n epsilon t is not fixed, so we get some kind of background speed caused by varying epsilon. Okay, so the equation has an extra term C here, which will be very important later. So again, we linearize at the zero section, and so sort of do the Taylor expansion of this expression. Then we see that we get roughly the heat operator applied on U should be equal to the Lagrangian angle of n epsilon plus the zeroth order term of C, which is roughly this like this. And so we get a derivative of epsilon in T here, and plus some quadratic error term. Okay. So C here is a constant that we can choose from. We can choose a constant that we work conveniently. So again, we need to see if we can do the perturbation. Yeah, so like the special Lagrangian case. But now we get a new term here, which is the zeroth order term of C. So this gives us hope to kill the obstruction by demanding epsilon t to satisfy the first order ODE. So to see this, again, we project the zeroth order term to the first eigenspace as before. So now let's choose C, this constant C, to be this quantity where V1 and V2 are the volumes of X1 and X2. So we project the zeroth order term in the Taylor expansion to the first eigenspace, and what we get is something like this, plus some smaller terms. So this term here shows that if this is zero, namely if epsilon satisfies this ODE, then we don't have this obstruction as before. Okay. So if epsilon solves this equal to 0, then the perturbation problem is unobstructed. So we can construct the approximate submanifold using this solution to this ODE. Then the balancing condition in this scenario is satisfied. Okay, so this is the idea why we can do the Lagrangian mean curvature flow perturbation. But we cannot do the special Lagrangian perturbation. Okay, so using this idea, we show that there exists a very large lambda and a solution U to that nonlinear equation such that this perturbed submanifold and epsilon t tilde given by perturbing the n epsilon by du satisfy the Lagrangian mean curvature flow, where this epsilon t is some function very close to epsilon naught, where epsilon naught is a solution to the ODE. So as epsilon t as t goes to infinity, this epsilon t will go to 0, namely the roller neck in the n epsilon t tilde will shrink to a point as t goes to infinity. So we get this kind of infinite time roller neck pinch phenomenon. So it is possible to generalize this result to the case where X prime has more components, more than 2 components, but then in that case, the Lagrangian mean curvature flow equation cannot necessarily be written into a scalar equation like what we did earlier. And the balancing condition will become a system of ODE rather than just a single ODE satisfied by epsilon, and which is this system of ODEs is not necessarily solvable. Okay. So finally, this is a picture illustrating the geometry happening here. So originally we have this black submanifold obtained by desingularized x1 union x2 using roller neck with scale epsilon naught t, where epsilon naught t is a solution to the ODE. Therefore, the balancing condition is satisfied, so we can perturb this submanifold by some exact one form du. Also, we need to perturb the scale epsilon naught to some epsilon t close to epsilon naught, such that this perturbed submanifold satisfy the Lagrangian mean curvature flow. And since epsilon t is roughly the scale of this neck region, we see that as t goes to infinity, this neck region pinch to a point. So it's our recent result, and we are still writing up the paper. So hopefully the preprint will release soon, then you can see more details in it. Okay, thank you for your attention.